joined by Volker Kölmel. Volker has started his professional career in the Engine Test and Commercial Center in the automotive industry at Porsche AG. Holding progressively senior roles at Cognex and now AMETEK Surface Vision, Volker has 30 plus years of experience within the surface inspection industry. He brings extensive product, industry, and application-specific knowledge to the market, and currently spearheads the development and implementation of new strategies to support a worldwide customer base. And with that, it's my honor to introduce Volker, and he'll be sharing his screens from here on.
Okay. Thank you, Michael, for the introduction and that we get the chance to talk a little bit about the challenges and benefits of surface inspection for AMETEK Surface Vision. Before I start with the technical part, I would like to give a short introduction about AMETEK. And AMETEK is a quite large company. It is known for global electronic instruments and electromagnetic devices. It's a company which has over 30 countries, facilities, 170 operation locations in all the areas. It is founded in 1930, and it's also listed on the New York Stock Exchange market. And it's even part of the Fortune 500, I have to say, in this case. To nail down a little bit more on the business units, so I mentioned before it was 170. A portion of this is dedicated to the battery industries. And what you can see on this slide is a couple of examples, but it's only a short number of BUs. You will find at AMETEK they play a role. For example, maybe Brookfield is known for the viscometer and rheometer for the slurry and so on. Then we have Solartron Analytics, which is doing battery cyclers and analyzers. We have Creaform for 3D scanners to double-check battery packs and so on, or LEND, for example, for non-contact temperature measurements. But there are many more, you can find where we play a role in the battery industries here. When you go to shows like here, you will find that not only a single BU is present on the show, we come in groups, so we have then also the opportunity to talk across the BUs. I represent AMETEK Surface Vision, and I will dive a little bit deeper into this. So we have, in general, two products. One is the Smart View technology, and one is the Smart Advisor. Today, I will talk mainly about Smart View because this technology plays a bigger role in the battery industry. Talking about AMETEK Surface Vision, really everything started in 1993 with ISIS controls, long time ago. This was then acquired by Cognex SISD. It was a division for quite a long time inside Cognex. And then in 2015, AMETEK required this division from Cognex, and since 2015, we are now named as AMETEK Surface Vision. Headquarter from our business unit is in Newark. And we have engineering centers also in the US and in Europe, and offices you will find across the entire world, so like Germany, China, South Korea, Japan, and of course, in the US. 30 years ago, or even more than 30 years ago, we started in the inspection industries, and we inspected everything which is a roll-to-roll process. So, for example, paper or metal coils, plastic nonwovens, lately the battery. The majority of our installation is still in metals and paper. So it's probably 2/3 of the installed base. And then plastic and nonwoven is the second bigger market. Really in the battery industries, we are probably the last 5-8 years, and maybe there are around 100 plus installations so far around the battery markets there. When I talk about battery industries, there are a lot of products or components which plays a role for surface inspection to look into it with different challenges. Yeah. So it starts from electrofoils like aluminum and copper foils. When you see those rolls, we call this coils. Those coils gets then delivered to the battery industries. It gets coated. Then we have other materials like separator materials, other battery industries like solid state batteries and so on. All this needs to be inspected to guarantee a certain quality. Lately, we introduced defect traceability. This becomes a must into the battery world. And we do not only inspect roll-to-roll application, we also inspect singulated parts at the end to help the customer to find defects in time. So we will not multiply the cost if it's found too late in the process. Speaking about the battery process, this is a typical value chain, how a battery gets produced. This is, for example, the lithium-ion world, where everything starts with the input material. Then we have the cutting process, cell assembly, packaging, filling, and then you have the output material, which is then the design. Is this a pouch cell or is this a prismatic or a cylindrical cell? This is the same process when it goes to a specific end product. So everything is a battery, but each battery, when it is reaching its final destination, like here or in the automotive industry or stationary storage and so on, has slightly different properties like energy density or life cycle, safety, thermal management. Everybody has a little bit its own environment to deal with this. This can then also end up in slightly different specification, what is needed from a quality point of view, and how we have to set up the technology in our system. And the surface inspection part is a camera-based technology which plays a role at the first three parts of the cell manufacturing. So we play a role in the input material, so on the substrates, cathode or separator material. Then when into the cutting, we play a role, and we play a role on the number three when it goes to some cells. When you look a little bit on the value chain here, you see how it adds value to the product. And our inspection system plays a role until the separation. And saying this, there is quite a big step from here to here on the value. And this is the reason is, when you find defect early in the process and you can reject or correct the quality before it enters the stack, then you only waste material cost and labor, I would say. But when it goes into the stack, it will then be much more expensive to reject the product later in the process. So this actually we define as a very strategic point to make a decision if a monocell or half cell or separator material is allowed to enter the stacking and the winding process. Let's talk a little bit more about the different areas along the process. So we will have different tasks along the process, and you can imagine on each of the process steps, like coating, where you apply the slurry on the collectors or on the drying, when you remove the solvent, and then the calendering, where you then compress the density, uniformity, and then later you have the slitting because you cut this in slits. So you prepare this later for the cell assembly, and then the notching, you separate this, or you have the singulation where you have then the individual pieces of the half cells or of the electrodes before it goes further in the stacking process. So each of them has a different challenge. So on the coding process, you have different line speeds. Then on the calendaring process, you are interested in different defects, maybe on the coding, maybe defects they applied on the coding. Then it can make a difference if you would like to inspect it straight after the coding, where the surface is quite wet, or you would like to inspect something after the drying. So this is one process typically to find defects when the solvent is left the coating and you have a reduction on the thickness. All of a sudden, you probably will see issues on particles and other defects, which was caused by imperfection of the slurry, for example, or you have kind of coating pinholes to the substrate and so on. Then the question is it a single side coating or double side coating? So there's a lot of questions. We have to look into it to define the challenges of the inspection system. Then on the calendaring process, there's a slightly different request for the inspection system when it comes to speed, when it comes to maybe different type of defects. So one example, it's here on the collector, it's outside the coating, when the calendaring process is not well processed, that you generate kind of wrinkles on the edge. So some customer call this angel wings. So this is an indication that the calendaring process has issues. Beside that, you have to inspect the coated area as well to see if you add any other kind of pinholes coming after the calendaring process. And then on the slitting, you are more focusing on the edge of the slit, edge burrs and so on. And then on the notching area, it really matters also what type of technology is used here. Is it a laser cut notching or mechanical notching? You can enter different type of defects. So the last image, what you see here are particles, which matters when you do, for example, laser cutting on the notching part, where the heat zone where you cut you can it's like a small welding process. Particle can jump again on the coated material and sticks out. And since the separator, which is the layer between the anode and the cathode, becomes thinner and thinner, so maybe today it's between 9 and maybe 12, 13 microns. Depends a little bit also on the end battery. I'm talking more about the automotive battery here. But if you have particles, they are bigger than 10 or 20 microns, and they're hard enough, they can penetrate the separator, and this can cause then shortages, and you get then a heat zone there. And this could then also lead to a bad quality. And in the worst case, on the lithium-ion process, this could also be a safety issue in terms of thermal runaways, for example. Here's an example about results first. So when everything is found out about your process, where the system needs to get installed, we have then to decide what type of technology we would like to enter. So in this zoomed in image, you see 2 cameras and a light beam at the bottom. And in this case, the customer has quite a wide copper foil. So this is an anode material where they coat multiple lanes. It's a continuous coating process where a customer is requesting to inspect all the individual coating areas, but ignore the substrate. So all this needs to be taken into an account what a system needs on capability to deal with all the circumstances here. On the left side, you see typical defects like devotes or particles or delamination or any other type of coating defects or imperfections. In the coating process, when you have, for example, it doesn't matter if it's single coated or double coated at the same time, the coating applies on both sides, typically on the top and the bottom layer of the foil. And beside defects, also the alignment part is a relevant factor, that the coatings are on top of each other, because when you later do the slit or the singulation of electrodes, you have to make sure on both sides everything is coated in the zone where it should be coated. So beside the inspection, also the alignment check is relevant. Next product in the battery is, for example, separator material. Here, the demand is a little bit different. What you can see here, it's a light unit, which is underneath the PE or PP foil in this case, which is a coated foil. And we have cameras on top of the foil, which needs to inspect defects. Like on the left side, you can see gels, or lamination spots, pinholes, and stuff like that. Scratches could be a challenge for transmission application sometimes. So therefore, in more advanced systems, beside the transmission view, what I call the king view, more and more system we have to equip now later with a reflection setup. So on the left side, you see this is the product we have to inspect. Then you have the light source on the top, on the same side where the camera is looking on the surface. And while the material is moving, we continuously inspect the surface. With the reflection setup, you have slightly different footprints of defects. So this is kind of blisters on the surface, which are hardly visible in a transmission setup, but with the correct orientation of light sources and using the right of cameras, you get a really impressive signature of this type of defect. It almost gives you kind of 3D effect, you know. On the right side, you see then colorful pixels of the defect, which are detected by the system and highlighted, and later it will be used to explain what type of quality you have on the surface. So beside this, there are also defects. They have more kind of characteristic of contamination, which is an issue, and also therefore the reflection setup is the appropriate setup to do. And when you're very careful with the light, you can also add more information to the contamination. This is like a tail event after a certain contamination, and to detect this as well and talk about this, you can be more precise in the classification, what type of defect it is, because it's not only relevant that the end quality is documented. The data are also highly used for the process people, and therefore it's good if the classification is more precise, because then they can use the data to understand how to improve the process. Separator by itself is a tricky part, because in the separator world, you have defects, and the gel is a very interesting subject here. You have a core part, and you have a tail and a head part on it. And what it also does when you use advanced light technologies, that you can also highlight stress in the material, which is also a feature which makes sense in some industries, because in the separator world, you have a single layer separator, but we also see multi-layer separators, and even multi-layers where you have 3 layers of separators between the cathode and the anode material. And then sometimes the middle layer is really hard to find those defects. But with the advanced light technology here, where we highlight the stress, this is an example of a picture from our system. Even middle layer separators, we were able to highlight the stress and find the defects in between 2 layers there. This is a little bit a challenge of the separator side. Then there are also solid state batteries, and each battery has its own parameters in world and speeds. And this is, for example, typical parameters when we inspect those surfaces, what are the requirements? So we have resolutions between 10 and 50 microns these days. There are web speeds and such lines up to 100 meters, and the web width can also vary from 100 to 1,200 millimeters. From the entry point of view, where we have the slurry part and the coating, this is very similar to the lithium-ion world, same process. We have to find the same defects, the same drying process is in place. But then straight after that, you have then an extrusion process where you apply the solid electrolyte. and therefore you have different type of defects you have to find. So you have to slightly adapt the surface inspection parameters or the way you illuminate and on this section that it fits to the needs on this type of defects. And then, of course, further down the process, you have the lithium anode, where you have to look for edge cracks and other defects, which plays a role to a certain extent to find the defects. On this type of process, really, we also found there is a high value not only to find defects along the process, also to control and monitor whether the individual layers, like this solid electrolyte layer, is on the right position of the cathode. It's covering the coated areas. It's not over covering the collector parts. So there's a critical tolerance where the layer has to lay on the cathode. So therefore, we do also kind of multi-edge tracking algorithm where we also control the layer and its position, for example. Yeah, typical defects on the solid-state battery are, again, coating bubbles. On the substrate, you can find edge wrinkles. This could also be a repeating defect, which gives the producer input from our system. What is the distance between the repeaters? So this could then easily identify what could be the root cause on which area in the process, this could become the issue. So they can get enough information that they can find out maybe where this is coming from, even if it's later in the process, then they have to go back, but they have a lot of data to analyze, for example, this. Then lamination contamination, okay. Or if the polymer is not on the area where it should be, or any other coating voids which is missing or not correct coated. All this are surface conditions which is not appreciated, and the customer needs to informed about that. If I go further in the batteries, so this is fuel cells, and also in the fuel cell, there are critical components. We do not inspect the fuel cell like it is here on the image, but we will inspect the material before when it's still on a roll-to-roll process. And typical surfaces is the PME material, like the polymer, electrolyte membrane, or the gas diffusion layers. Those kind of surfaces needs to be inspected if there are any wrinkles or any other coating spots or any other quality relevant defects which should not go into the final fuel cell. Also, this is the target of our inspection solution, which requires the correct lighting and camera technology. One side step to the battery is when we talk about inspection on blanking. So when you build a battery pack, blanking lines plays a more and more crucial role. It becomes more and more interesting also to inspect those plates on defect. So therefore, we had to develop a software which is capable to identify the shapes, what is on web, what is off web. Like here, you have square shapes, you have rectangular shapes, or you have square shapes with holes in it. And the software has to identify what is off web, that is the black background, or on web, and what are the defects. Also, this is an area where we help to make sure that the quality is well detected. So what I've shown you so far are end results of all the work we have to do now to talk about the challenges of a surface inspection system. So let's dive a little bit into the technology by itself. So the material is on focus for our inspection system here. So we have to understand about what is the line conditions, what type of light configuration we have to find. what are the cameras, where are the position, what the geometry we have to choose to make defects really visible here. And then behind, you need a system architecture and a software which allows you to deal with all the different surface conditions. When we get a new project with customers, everything starts with the material and with the process itself. So actually, there is not much we start to ask. So our typical question is, what is your web width? What is your line speed? And what is the smallest defect you are interested in? This is our starting point, and then we share in general our application questionnaire when it comes to the point that we request samples from you, that we can also qualify our recommendation that it fulfills the requirements of your need. And this is purely when we talk about the arrangement of lights, cameras, and so on. But we have to look further because we do not only sell cameras and lights, we sell solutions here. So therefore, we are very interested about your environmental situation. That means what is the space we can use in the system? What is the other environmental? Is this a dry room? Are there contamination and so on? So there's a lot of questions, which leads us then to think about what kind of sensor we use. So on the right side, you see a typical camera. This is a line scan camera. So you can see it's only a line. So we scan the surface, and while the material is moving, we do one infinitive image of the entire roll or coil, it's also called, on the substrate. Those are typical sensors we use in different combination. So it could be a one camera combination where the customer asks us to inspect the electrode material and the substrate, for example. This could be very challenging because on the cathode, for example, you have an aluminum surface, very reflective. At the same time, you have the coated material, which is almost infinitive black. So this is at the same time, I have to look with the same camera of both scenarios, and I have to find a way how to deal with all those optics. Yeah? And therefore, you have technologies like HDR, stands for high dynamic range technologies. We also use multi-channel illumination. So you have a camera on one position and you have multiple cameras around the surface. This helps to identify different defects on different positions. So we have also the flexibility to use this. Or you have a camera with multiple light sources, and this is called time-based multiplexing, where one light after the other will strobe, and we take images from all the individual lights. And then we have a composed information of all the different illuminations and how the defect looks like. Lately, we also included CIS technology in our toolbox. CIS stands for contact imaging sensor. So the beauty of this one is it's a very compact sensor. It's very close to the surface. It requires minimum space, mechanically wise, that it fits into battery lines. Because even today, we find areas where the inspection part was not really thought about when they started to design lights. So sometimes later, we had to find areas where to include this. And this brings us to the next point, where we try to find the location where to inspect. So we prefer actually to inspect on a roll to have a very stable surface condition. So if we have defects on the surface, then when the light becomes a different signature, it's very unique, and the defect gives us a really good contrast versus the background. So in those cases, most of the time we can use collimated lights or side lights or any other concepts. But sometimes we are also forced to go, we call this now open web, where we are between two rolls. We have to inspect. Now we have to compensate sometimes a little bit web conditions like small pass line variations or other dynamics. So therefore, we have to use different lights there. Maybe it's a more diffuse light areas and any other lights. on that. So finding this is also one of our challenges here, what to use on light quality, but it will also lead us to think a little bit more about does wavelengths matters. And we also found in some application that there are benefits if you go to certain wavelengths to make certain defects more dominant, or we can even hide stuff or make stuff more transparent when you think about separators and so on. So all this plays a role to design or to tailor the system for your industries. When it comes to optical configuration, then we have the choice, as I mentioned already before, do we go on a direct reflection setup? Is this in benefits on this process, on those defects, or it's more an indirect reflection setup like dark field or side lights or transmission lights, when it comes to the separator. So if all this is found out and tested and designed, then we have to go further into our architecture. So all the work we have done now leads us to an image where the defect versus the background should have an optimum contrast. So this is done. Now, when we have done this, now we need an architecture and a software which is segmenting the defects from the background. Found a pixel of interest. Those are the red coded areas. What is the defect here? And when this is found, then we have to classify to describe this. So in this case, you see this red box, it's around the defects. We will calculate more than hundreds of features to describe this defect, to classify the defect, that you have also a name on it, because based on the classification, you have now the capability to recheck defects or mark defects in real time based on class names, for example. It is also important the defect data management, because you will get a large volume of information from us. Each defect has several hundreds of features we have to talk about. Then you have certain orientation of the individual slits. You probably would like to grade slits, and there's a lot of more things to do when it goes forward or when you have to start to think about the yield management. All this is also in the package to give you enough information, real-time interfaces where you can retrieve data, or we help also to recheck in this case. When it comes to the surface itself, we have the inspection of a solid surface. So the software should be capable to inspect, for example, this again would be separator material. Then we have a surface which has a line structure in it, like the continuous coating, where you have the coated and substrate areas on top of it. So the software has to deal with this. Then, of course, you have also intermediate coated material. It's reduced demand, I have to say. So over the years, I think the continuous coating is a little bit leading, at least from the request we get, but still here, it's a significant amount of coding we have to help. And when you do the intermediate coding, then afterwards you have also to inspect sheets, like I've shown before on the blanking lines. And when it comes to the notching and the cutting of half cells or cells, we cannot only rely on square shapes. So we see cells when they are notched or cut, they have kind of radius on the edges or funny shapes. So we had also to develop a software which is capable to deal with all the different forms, which probably ends up on a final shape before it goes into the stack. This is, for example, a user interface, how this could look like, where we identify on those blue sheets the coded area, and you see a little bit of shape, so you understand what is behind. And when we find defects, We will also tell you if the defect was found on the coded area or it was found on the substrate area. And this information can also be later used in the classification. Say, well, I would like to have a unique feature when it is on coding or off coding. So this is when we talk about defect detection. But beside the detection now, customer also wants to have kind of a with monitoring. So you have now an image of the surface. So in this case, it's a coded area, and then you have to collect on the right side. And the customer was interested about uh, the coding lane width and the substrate lane width. And since we have a continuous inspection, this is a relevant factor, what we can also show then to the customer. What is not part of this presentation is the calibration part. Also, this has to be, you have to have good tools and techniques and calibration rulers that also measurements for the width will take into account that the number fulfills the specification of your needs. When we have, let's say, top and bottom view inspection, we do not only measure the top surface and the coating or substrate. In this case, we will also do an alignment check where we tell the system where are the edges or where's the coating on the substrate between top and bottom. So here, for example, there would be an off and would fail the alignment check. And if this is the case, we will warn you. This type of request is mainly on the coding process because here you can directly influence if you see that alignment is running out of your spec, that you can do the correction. If you monitor this later in the process, then it's still important to know because when you notch the cell, you have to make sure everything is totally covered with the coding area. But you cannot really change the process here. So it's a strategic decision. What else we can do with the alignment check or with this monitoring? This is now on a winding situation. This, I think, was a prismatic cell where you have a separator, then you have the cathode material, then the other separator, and then you have the anode material. And in this, hang on a second, in this process, they will wind, they will cut. And the task was here to have a light unit in a reflection setup on the bottom, which the camera will see probably the separator, the cathode, the separator, the anode. And on the left side, you see the example here, So for example, this is the aluminum collector. Then we have the separator, which is on top of the cathode material. This is the cathode underneath the separator. And on the opposite side, it's the separator, and you see the background of the anode, and then you see the background of the copper foil underneath the separator, and this is the copper foil. And all here you see the different scenes. So this is a lighter line here, this is a darker line here, and so on. And with a specific light wavelengths, we can penetrate a separator, and we can then measure all the positions of the individual layers and help also here to do an alignment check when this prism or the jelly roll gets winded. So this is also an example of what we can do here. What else we have to do when we do defect inspection? We do the WIS monitoring, we have the alignment check. Lately, we have now also to look into the traceability. So therefore, customers are using this kind of data matrix codes, or also sometimes called fiducials. So the system will inspect the surface, it will detect the codes, it will detect the defects. We will then decode those data matrix codes. We will know about the information, what is on the code. It's a unique code in this inspection file. One other great feature on such a DMC code is this L shape here. Okay, so you see the yellow circle. This is the coordination 0 point on such an DMC code. This plays a crucial role on the next slide I will show in a second. Uh, Talking a little bit more about the coding itself of the DMC codes, there are inkjets and or the laser engraved codes. I have to say, when the code has a certain size, if it goes down to maybe only 3 or 4 millimeters, you probably will only see the laser engraved codes. If there are bigger codes possible, then also the inkjet code might be applicable. So each of those has pros and cons. Going for a little bit further, and talking about this 2D data matrix codes. So we talked a little bit about the process along the lithium-ion process. So you have the input material coding and so on. Let's assume you have only an inspection system on the coding. We will then also detect the code. We will decode this. Everything is in our inspection file. You will have an absolute information between the code and your defects or your cell. And when you would have multiple inspection systems along the process chain, we will inspect this coil on a later stage in the process again. We know already about the inspection from an earlier, and we can use the data we found here and introduce this also on a later process step here. So we can overlay the defects. We can transform the coordinates because we know what is the beginning, what is the end, everything we can decode out of such a data matrix code. All this information is available to your MES system. So that means the manufacturing execution system, when you get a kind of a claim, or you have to go back to understand what cells are in which pack and so on, are with this ID of the data matrix code, which is unique for this inspection file, you can everything nail down to the source of each individual electrodes, which plays more and more also a crucial role in the battery passport, where you have the full tracking of data all the way down to even to the slurry and further down, but also here on the inspection area. This is a user interface where you see on the right side kind of a streaming video from the cutted electrodes. You can then click on a certain defects, which gives you then a pause of a defect where you can review the defects on the different illumination. You get all the features, the classification. Then you get defect summaries of the entire coil. You can filter that you only would like to get displayed certain type of defects here. This is really a powerful tool, I would say, for the process engineers to get information about the distribution of the defects. Is this on a certain area and so on? There's a lot of data what is available here to analyze also backwards your process. Talking about this video console on the right side, this is a very, how should I say, interesting tool for us. It's called streaming video. What we do here is we take with the same resolution what the inspection system is doing for the defects, we record your entire coil, the entire roll. Yeah? And we compress this, but we do not lose image quality here. And while we do this, we can store data for several days. If you have very interesting coils you would like to keep for longer, you can lock the coils or you can archive the entire coils further away. Because here you have now the possibility to have a virtual recoiling possibility where you can zoom in on defects, zoom out on defects. You can even look in areas where the system probably has not found any defects, but you still have images of the entire coil. This plays a crucial role when you have to scale up sometimes, because in some of our application we are working on pilot lines, and pilot lines does not run 24/7 all the time. So therefore, in the time, when no inspection is running, you can still use those coils, for example. You can load the coils. You can rerun the coils with different settings. You can train the system on coils you have recorded, so you don't have to wait. You can continuously help to optimize your product. You have not to wait. Or if you get a claim and the system has not found the defect, you can go on this area and analyze and change the parameters that next time this is then detected, and you can rerun this call to prove if your change brings this to the point. We learned this helps a lot to speed up the process, to make it really user-friendly for our customers in a minimum of time, to do a maximum adjustment to the system. When all this is done, we are still around. And what you can see here, this is our global application support area where we have various programs, preventive maintenance. So we help that your system is always available. So there are remote and direct support possible. On the remote one, it's a little bit difficult in the battery industry because everything is really secret. So this is something we have then to discuss with customer by customer. What is the way that there is a way that we can help fast, not only when you have problems with the system. It's also when you need application engineering support. You would like to discuss with us defect parameters and how to do other things. So we are available for you 24/7. And to summarize all of this, it's a long journey, I know. But in principle, we have clearly to understand the process, your specification. It's sometimes complex, but it's solvable if you have a modular technology with all the different products like lights, cameras, and so on. Then we have to talk about your strategic points to maximize the quality and yield. It's the primary thing. But on the other hand, we have also to understand it's always a trade-off between technical solution and commercial solutions. So there's also trade-off where we have then to work together to find the best solution for your requirements, that this is then applicable for you. I have also to mention that the system is very modular here. That means even when we start with a simpler system with less resolution, or you ramp up the speed, you double the speed in 2 or 3 years, that we can start with a simpler system, but it's very easy to upgrade the system then to the new performance without big changes typically on your infrastructure and so on. And what you also need are tools like streaming video to help you to speed up the process in your environment. Saying this, if you have further interest, feel free to visit us on our website or sign up on subscribe on our latest newsletter here. And I think I'm now on the end of my part of the presentation, and I'm more than happy to answer your questions if there are some. I understand it's a lot, but it's a complex field, and I try to scratch each part of the individual process a little bit, that you get a small teaser to reach us out for more in-depth information.